Okay, hello and welcome back everybody. We are moving on to sections 9.4, 5, and 6. Fortunately, we are shoving all of them into one section, and I know that seems like a lot, and it probably is a lot. We're going to be okay. It's, in many ways, the reason why I'm shoving them together is we're going through the same procedure that we went through with the Laplace transform. We're just doing it with the Fourier transform now. So we'll see how it's constructed, and then we'll see how to solve some differential equations with it. But we're going to jump through it a little bit faster since we've already had some practice with the Laplace transform. And they're kind of doing the same thing. So if we kind of jump back to, let's go back to even the very beginning of the chapter, where I was talking about fixing these problems of the Galerkin truncations. And the second one, basically, we're gonna take the interval over which we are calculating the Fourier series, and we're taking epsilon to infinity, so we're pushing that interval to minus infinity to plus infinity. So we're making an infinitely large interval over which we're calculating the Fourier series. And in doing that, we can kind of go through the same song and dance that we did with the Laplace transform. But with the Laplace transform, we fix the bottom integral bound at 0 and the top integral bound at t1. And in this case, I'm going to fix the bottom one at minus x naught and the top one at plus x naught. So it's a symmetric integral around 0. And this is actually a requirement for calculating the Fourier transform like that. But why am I doing this? Why make it symmetric? Well, you'll actually recall when, in maybe Calc 2 probably, when you learned about these improper integrals from minus infinity to infinity, they were defined by the limit as L went to infinity of minus L to L. So they were defined symmetrically, and that's why we're defining it symmetrically here. If you want to define it asymmetrically, that's perfectly valid, but then you're not really dealing with these sorts of integrals, and then you kind of have your own new version of a transform. So we make it symmetric, and then we're going to play the same game that we played before, where I'm representing this a sub n, which is the entire calculation there, inside of its reconstruction for f, right? So that's saying that, you know, this f here and this f of y there are the same because I'm just plugging the a sub n here in all the way down there by its definition. And then I'm going to recognize that if I'm taking a limit as x goes to infinity, I'm taking a limit as n, capital N, goes to infinity in my sum. And I'm going to do the same thing where I make some coupling between the x that I'm letting go to infinity and the n that I'm letting go to infinity. And if I let the x naught be pi n to the 1/2 power, then what I recover is a 1 over 2 pi out front. And then this 1 over n to the 1/2 power, which you'll recall, this behaved like dx. I mean, it was dt in the Laplace transform setting, or ds even. But it behaves like dx, or I guess maybe in this case we'll say it behaves like dy or dx. I don't exactly know which variable I use, but it behaves like dy. And then these bounds tend to positive infinity and negative infinity, and these also tend to positive infinity and negative infinity, and these will behave like y. So we're going to recover an integral once again. The integral looks like the following. It's 1 over 2 pi. Then we have an outside integral. I used ds there, and it should not be ds, dy. So I have an outside integral from minus infinity to infinity, divided by 2 pi, dy, e to the iyx. And then I have an inside integral, e to the minus iyx, dx. And so really what these integrals look like is I have two integrals that are in some ways complex conjugates of one another, right? This is like the inside integral, and then I have the outside integral, and they look the same up to a complex conjugate. And especially if we decide to write that 1 over 2 pi as some roots, right? I can split my 1 over 2 pi into two square roots, and then I define a very symmetric inner integral versus outer integral. They almost look the exact same. The only difference is that the inner integral I'm taking against e to the, I have my signs wrong here, which makes our life very easy. Oh no, I did that right because I put them in the wrong order. I put them in the opposite order. So this is the outside integral, and then this is the inside integral. And what we get out of that is that we define something from the inside integral as the Fourier transform of f, and then the outside integral reverses that. You can think about this capital F like f hat here. So basically the outside integral reverses the inside integral, and they behave very symmetrically, which is kind of nice about the Fourier transform that you don't receive out of the Fourier series, right? In the Fourier series, we have a sum which reconstructs an integral, right? I evaluate the a sub n's and I get an integral. I have to use an integral to do that, and then I can reconstruct my function with the sum. So there's this little bit of strange duality there, versus if I jump over here, these are like almost exactly the same operation on each other. So there's some sort of inherent beauty to the Fourier transform, where it's just the transform itself is almost its own inverse. It turns out that actually it's if I transform to the 4 times f, then I get f back. So it's kind of like I in the sense that it's its own quadratic root, but no other roots. So jumping down, we can see our actual definition here. The Fourier transform is defined as the following, and we're going to use this notation of a hat. So I'm going to put a hat on top of my function. This is a very common notation, so the hat. Very, very common notation to denote the Fourier transform. You put a hat over the function, and this is no surprise that the space of functions for which this is defined is exactly the L2 functions that we were talking about earlier. For Fourier series, it's the L2. The Fourier series is L2 functions, the functions which are square integrable over a finite domain or a compact domain. Here it's just the functions that are square integrable over the entire real line. The inverse Fourier transform looks almost the exact same as I was hinting at the whole time. And then we can construct representations of linear operators with the Fourier transform as well. And actually their representation is a little bit easier to compute because we don't have to play that weird song and dance with the complex integral. Remember in the Laplace transform we had like gamma minus I infinity and gamma plus I infinity in this representation? Here we do not have that anymore, so we can get away with a much easier representation of our operators in the Fourier space. And this makes my life easy when it comes to derivatives too, because I don't pick up any of those, what did you call those? They were the initial value terms, so don't pick up initial value terms, which is great. All we get, the symbol of the nth derivative is iy to the nth power, so that's very useful, right? And I'm going to represent the symbol with a hat here as well. It makes a lot of sense. If I'm transforming that operator, that's how it gets represented. And then the multiplication operator is still almost just as bad. If I'm multiplying by a monomial, I'm still picking up n derivatives in the Fourier space, and actually I have n powers of I out front as well. So this can be almost as bad as in the last case, because once again, that means if I decide to multiply by a function, then I'm really computing that entire function's worth of derivatives on my Fourier transform, which is not the greatest thing in the world. Although, just a quick aside, this concept leads to the idea of what's called pseudo differential operators. So there is actually a really good use for this, even though it looks kind of ugly. We have this notion of pseudo differential operators because of it, because you can kind of tell, right, the multiplication by g is behaving like a differential operator over here, but there's infinitely many of them, and so you get some really strange behavior because you technically have infinitely many derivatives on the right hand side, and so that's where these pseudo differentials show up instead. So basically just with the Laplace transform we have the same sorts of problems that we can solve that are a little bit broader than maybe the regular ones we knew how to solve in the past, but not that much broader. So we can solve ODEs with polynomial coefficients, higher dimension systems, impulse forcing. So this is going to be just like when we had our heaviside function in the Laplace case. We can do that with the Fourier cases as well. And then actually PDEs is really the important thing for Fourier transforms. A lot of times it won't get talked about in an ODEs course. It'll only get used in a PDEs course because we really do use these all day long in PDEs, and we don't really use it in ODEs very much unless something interesting is happening. But we're introducing it here just because it's something good for you all to know before you graduate with your math degree. So jumping down to the next example, we start to see the delta function show up. And since we've already talked about the delta function, I won't talk any more about it. Go see the last video if you want a refresher on the delta function. But in particular, I have derivatives on the delta function. So I'm taking, if I Fourier transform a monomial, I end up with n derivatives on the delta function. So that's kind of something important to know. And it's a formal derivative, right? So that's a formal derivative in the sense that, once again, this is not a function. It's a generalized function, and derivatives on a generalized function don't really have that much of a meaning, except when you put them into against another function that's an integral. And then all of a sudden this has perfect meaning. It's just the sifting property, and we get n derivatives on f with the sifting property. So that's really how it gets defined as the nth derivative there. All right, so let's talk about how we might solve a BVP with the Fourier transform. I'm going to start here with just saying, fine, if we've pushed our boundary values to infinity, let's just make the assumption that we have a boundary value problem with boundaries at infinity, and we're quote unquote periodic at infinity, whatever that means. So suppose we have a differential equation which has some behavior at infinity, but it's like a boundary value problem, but the boundaries have been pushed all the way out to infinity. Then we solve it the same way that we did with the Laplace transform, where we just compute the symbol here, which is the symbol there. And so we compute the symbol of that, which looks like this, and then it has some sort of inverse that you can calculate in Fourier space, and then we're going to act it on the Fourier transform on the right-hand side here, invert it, and then inverse the Fourier transform, and we'll recover y out of that. Or I guess I should call that phi, shouldn't I? So I'm working in phi now. You'll see up top. I'm working in phi. The reason I'm working in phi is just because when I defined my Fourier transform, I defined it with y as the conjugate variable, and I don't want to confuse you by using too many y's at the same time. So phi will officially be the function which I want to solve for in my differential equations. You can see the same steps that we had for the Laplace transform, just now translated to the Fourier transform. All right, so we'll jump ahead to solving some smooth boundary value problems with the Fourier transform. And I'm going to start just with the convolution. So in the Fourier space, the convolution changes a little bit. So there's this same idea of f and flipping and translating g and then integrating everywhere. But we've gained now a 1 over root 2 pi, which is understandable because that was in our original Fourier transform as well. But instead of integrating from 0 to t, or in this case, I guess it would be 0 to x, instead of integrating over some finite interval in the Laplace transform setting, we integrate over all of space. So integrate over all of space in Fourier convolution. So this is important, right? Because convolutions are actually defined dependent on a function space. You can't get away with defining convolutions the way we do with like multiplication, where you kind of have this independence of the space that we're working in. Multiplication behaves the same way. Convolutions care about the space of functions that I'm in. So if I'm using the Fourier transform, this is the convolution that I use. If I'm using the Laplace transform, it looks similar but not exactly the same. I have a slightly new convolution. And in the previous section, there is the perfect, well-defined definition of convolution independent of function spaces. It cares about their domains and whatnot. But for now, we could just think, okay, if I'm working with the Fourier transform, this is my convolution. If I'm working with the Laplace transform, we go back and we look at that convolution. And the tables at the end of this chapter agree with that. They have both convolutions in them. Okay, so we have the same properties of convolutions that we had before, and in particular, the transform of the convolution is the multiplication of the transforms. This is, once again, the most important, this is the only reason why we define convolutions, is because it has this beautiful property of, in a transform space, it's multiplication, in the pre-transform space, it's convolution, and vice versa. They're dual in that nature. Okay, so now I get to this next paragraph that says, because I jumped up here, I said, oh, let's just assume that we have boundary values at infinity, but at the end of the day, the whole reason why we did this, one of the main reasons we did this was because we didn't want to solve boundary values at infinity. We wanted, our Galerkin truncations weren't working for us to solve regular boundary value problems. So this better be able to help us solve regular boundary value problems. And so that's what we're going to see here. So what you can do to solve maybe a more traditional boundary value problem, this is just a second order boundary value problem in one dimension. So I've got my two boundaries here, and they have some specific values, and x0 and x1 are finite, right? What I have to do if I want to treat this boundary value problem in Fourier space is I consider the solution to my differential equation, phi, actually as some other bigger function phi, which I'm calling phi total, and then multiplied by these heavy sides, because what is this actually saying? This is saying, hey, phi of x is actually piecewise. It equals phi tot between x0 and x1, and it equals 0 everywhere else. And so maybe, I have 0, and then I'm up here, my function does its weird, crazy thing. Maybe it comes down there, and then I'm 0 again. And this is the behavior of phi of x. And this is a perfectly valid function for me to take a Fourier transform of. But once I do that, once I take the Fourier transform of that, things get a little bit ugly, right? Because I'm considering the Fourier transform of a multiplication of functions, which means I'm considering the convolution of phi tot with that really big ugly thing, which I have described down in the table. It doesn't look exactly like this, but it can look like this if you modify some things around. There are different ways of representing the Fourier transform of the Heaviside function, but this is kind of beside the point. What I'm trying to say is that we don't really want to do it this way. If I go through then and calculate my derivatives, I end up having three terms on the second derivative, which I have to take convolutions of, 2 terms on the first derivative, which I have to take convolutions of, and the 1 term on my last derivative, which I take convolutions of. So this is actually not the way that we want to solve BVPs with the Fourier transform. We can get away with something a little bit more clever. And if we have an nth order BVP, okay, this is my nth order there, and it's a BVP, it's my n boundary conditions, then what I can do is give myself n derivatives of delta functions at the boundaries, and then give them some arbitrary constants. So by adding these n derivatives of delta functions at the boundaries, what I'm saying is, hey, let's solve for just a generic function phi, which has its own thing, and then let's go and give it some weird delta function properties at the boundaries, and then depending on how we choose c, we can kind of shift phi around until it actually agrees with the boundary values. We can talk in class about how we would actually derive that. It has to do with something called the Volterra integral equation related to this boundary value problem. But this is maybe a better way to do it, because the CJs are arbitrary. And what we're going to do once we just solve this top ODE with the CJs there, and then we have a system of n unknowns, and we have a system of n boundaries. And if you have a system of n unknowns and n boundaries, you'd be able to solve them for satisfying everything. So let's see how we would do that in practice. See how we do it in practice. Let's take phi double prime plus 4 phi equals 0, and then we have some actual finite boundaries here. So phi at -1 is 1, phi at 1 is -1. Okay, so we're going to follow this idea up here. It was a second order differential equation, right? So I'm going to need j equals 0 derivatives on delta, and j equals n minus 1, so 2 minus 1, j equals 1 derivative on delta. Okay, so I need a 0 derivative on delta. There it is. C0 on the 0 derivative on delta, C1 on the first derivative on delta, and my boundary conditions just sit along for the ride. And then if I take a Fourier transform of phi double prime plus 4 phi, the double prime turns into iy squared, right? We don't have to worry about initial conditions with the Fourier transform. It just becomes iy squared, and the 4 turns into 4, believe it or not. And then when I'm computing now my Fourier transform of the delta functions, we just jump down to the table of Fourier transforms, and I find my delta function, and I see that a shifted delta function is e to the I x naught y. And then to gain just the delta function, I could divide by 2 pi to the 1/2. So I'm going to get e to the minus I x naught y here, if I can find it. All right, it's right there. So I have e to the x naught was -1 and 1, so e to the -1 iy, e to the -1 iy, all over to the 1/2, and then I'm doing the same thing here, except I have a derivative, so I have to account for the derivative in the delta function. So I mean, we can also see this down here, where if I take a derivative of the delta function, that would be like me right there. So the derivative of the delta function gives me an iy out front, minus iy to the nth out front, and then the shift is what's giving me the exponentials. Okay, so jumping back here, I have my exponentials and I have my iy out front, and then I've solved everything for phi hat, right? If I factor out phi hat, I'm dividing by what is iy squared? That's -y squared plus 4 phi hat. That's what the left-hand side looks like, so I'm going to divide both sides by 4 minus y squared. That's why I have 4 minus y squared in the denominator there, 4 minus y squared in the denominator there. And now I'm going to want to take the inverse transform of these two functions. Now it's not that easy to be able to tell what the inverse transform should be, but if I jump down to my table, we look at this one right here. So e to the, or this one even, they're kind of the same. So if I have something like lambda over lambda squared minus y squared, which in our case we had 4 over 4 minus y squared. Oh, this should really be a 2. 2 over 4 minus y squared. That means that it's going to inverse transform to this, except we had something out front, right? We happen to have e to the iy minus e to the minus iy all over root 2 pi, multiplying that, which means that we have to consider a convolution. So a convolution of this function with what is the inverse transform of something like that? Well, that was the delta functions, you'll recall. So it's a convolution of that with the delta function x minus -1, convolution x minus -1 minus delta x minus 1. And when I compute a convolution of those two, then what ends up happening is I gain some shifts. But, right, so here's the shifts that I would gain out of the convolution. H of x plus 1, h of negative x minus 1, h of x plus 1, h of x minus 1. So these are the shifts I gain out of convolution, and same with the cosine terms. This would end up being cosine according to my table, and then it's convolved with some delta functions. And so we get these shifts on the sines and cosines, but if we get a little bit clever about the interval we care about, the interval we care about is -1 to 1, and within that interval, the h x plus 1 term right here is equal to 1, h of minus x minus 1 term here is 0, h of x minus 1 here is 0, and h of negative x plus 1 here is 1, and so what we get actually is really a 2. This whole thing becomes 2, and this whole thing becomes 2 in that interval, right? You gotta be clear that you're only considering that interval, but you can absorb that 2 into the constants, and so we see that we recover sine squared and cosine squared as our fundamental set of solutions. And you're all going to be really mad at me because you're going to be wondering why you didn't just solve that with your characteristic equation. I agree, you probably should, but this is just a way to get us used to using the Fourier transform. And if I gave you something really, really complicated right away, there's no way you'd be able to use the Fourier transform. So that's why we got the sine and cosine, and then we just use C1 and C2 to fit our boundary conditions, right? -1 and 1. So upon fitting the boundary conditions, we get negative cosecant 2 sine 2x. Okay, now we're going to shift our focus to BVPs at infinity, because these are also important. And I can look at the two-dimensional BVP here now, and this is actually the same two-dimensional function we were looking at before, which had some initial conditions in the Laplace case, but now I'm going to give it boundary values at plus or minus infinity rather than an initial condition, and we'll see that our solutions are completely different, which makes sense because boundary conditions matter a lot. So anyway, we represent this as a matrix vector equation. So I'm just going to call phi the vector phi1, phi2. So I have two derivatives on that. I have this matrix interacting with the vector phi, and then I have my additive function 1 and -1. And if I go through taking a Fourier transform of each term, phi double prime ends up being negative y squared phi. Because once again, this is iy all squared, and the I becomes -1. The phi just transforms to phi hat, and then the Fourier transform of 1, if I jump down to my table here, Fourier transform of 1 is root 2 pi delta. Okay, so 1 on one side becomes root 2 pi delta on the other side, and so I get root 2 pi delta in front of my forcing vector. So once again, we can isolate phi, this should be a phi, isolate phi to the left-hand side, phi hat, and what I'm going to get is the same sort of behavior where I have to represent everything as a matrix on the left-hand side, and then I have it on the left, and I end up dividing by it, or inverting, considering some matrix inversion there. What I end up with after simplification is root 2 pi delta over 2 minus y squared, and then the vector -1, or 1 minus 1. Now, I want to comment before, let's just take the inverse Fourier transform of this directly, and in particular we're going to take it of 2 pi to the 1/2 delta y over 2 minus y squared directly, because of the sifting property of delta. Since delta has the sifting property, if I represent the inverse transform of that directly, the root 2 pi cancels with the root 2 pi out front, and I'm considering an integral minus infinity to infinity of delta y e to the I x y divided by 2 minus y squared dy. The sifting property says I'm going to evaluate every y I see at the shift on the delta. Well, how much has delta been shifted? It's been shifted by 0, so I'm going to evaluate at y equals 0. Sifting says evaluate at y equals 0, which gives me e to the 0 is 1 divided by 2 minus 0, and I recover 1/2 as my solution. So this is phi. Well, it's phi, multiplying the 1/2 by the vector there, 1, -1. Okay, so phi is really the vector 1/2, -1/2. There it is. It should be a function of x there, not a function of t. But let's just jump back up to the original ODE and ask ourselves, man, we went through a lot of work just to find out that this solution to this is constant. But it is, because let's think about it. What is, if I let phi be, let's say phi1 is 1/2, and phi2 is -1/2, then does phi1 equal its value on one infinity versus the other infinity? Definitely. Does phi2 equal its value at one infinity versus the other infinity? Definitely. And if I compute negative phi1 plus phi2, I get -1/2 plus -1/2 is -1 plus 1, I get 0. And what is two derivatives of phi1? It's 0, because phi is a constant. And then I would do the same thing there, and I would see that that's satisfied too. So in fact, this was a lot of work to find out that our solutions were constant with 1/2 and -1/2. But I don't know upon initial inspection that we would have noticed that. It wouldn't have taken too long to figure it out probably, but it's really kind of cool to see the Fourier transform give that to us here. Okay, let's skip this next one, but it's kind of a cute one if you want to take a look at it. But we're going to move on to solving some non-smooth boundary value problems with the Fourier transform. So we have to start with this very, very lovely theorem that the Fourier transform of the Heaviside function is a shift divided by IY, and then you pick up a delta function right in the middle. So this is a really kind of weird sort of thing to be happening, Fourier transform of the Heaviside function, but we do have to use it when we incorporate our Heaviside functions because they're necessary, right? They're necessary for us representing these sorts of behaviors in non-smooth boundary values, or not non-smooth ODEs. And so if we start with this ODE, then to manipulate the right-hand side, we represent the right-hand side in terms of Heavisides once again. And when we do that and simplify, we get negative Heaviside of x plus 2 Heaviside x minus 5. It kind of makes sense, right? There's there's 0 to the left of everything. There's a -1 between 0 and 5. That's accounting for this negative Heaviside. And then there's a 1 between 5 and infinity. And what is the difference between -1 and 1? Well, the difference is 2. So you have to jump up by 2 once you get to 5. So that's what the right-hand side looks like. And if you go ahead and use this definition for the transform of the Heaviside function, then when we transform both sides, the left-hand side still becomes negative y squared plus 1 in this case, negative y squared plus 1. But the right-hand side, we have to play with all of these really ugly terms that the Heaviside gave us. Step 2, thankfully, is already complete. In step 3, we factor out phi hat to the right, and then we divide by 1 minus y squared. Right, we divide by 1 minus y squared. So once again, my spidey sense is telling me that this should look something like sine, right? We should see sines and maybe some cosines here, shifted perhaps by 5. And I have to play with my table below until I can get something to work out. Something to work out for me. Or you can plug it into your computer, right? You use something like inverse Fourier transform on your computer, and if you put that in to inverse Fourier transform, you'll get sine squared x over 2 in this region, and then a sine squared x minus 5 in this region, and actually everything's subtracted by 1/2. So what does this look like? It looks like that. So once again, just like the Laplace cases, you get something that's smooth. So the solution is a smooth function for a non-smooth behavior, but I think everybody can kind of tell that something weird happens there and something weird happens there, which is at 0 and 5, just like you would expect. And it's because the solution has to account for basically the switch is getting flipped at time equals 0 and time equals 5. And then if I scroll down a little bit more, let's just verify that we've solved the boundary value problem. If I take two derivatives on phi plus phi, does this equal 0 to the left of x equals 0? Yeah. Does it equal 1 between 0 and 5? Yes. And does it equal -1 between 5 and infinity? Yes, it does. So, it's interesting to see the Fourier transform give us solutions to problems that look so tricky. But you might be asking me, hey, then the boundary conditions are not satisfied there, because you said, right there, you said that phi on one side was equal to phi on the other side. And actually, I should have written in here, since it's a second order problem, maybe the derivatives too. But the boundary conditions are not satisfied, you're going to say. And there's this really weird thing in math that you're probably going to have to save for graduate school if you end up attending graduate school, where the solutions that we obtain with the Fourier transform are what are called weak solutions. This word weak right there. And weak solutions have very special properties. Like, for example, as long as this is not unbounded, if my solution stays bounded on both sides, then technically the limit is 0 in the weak sense. And I know that feels really weird, but what that means is that since the limit is 0 in the weak sense, that the boundaries actually do agree with each other. And it's just because there's this really weird thing that happens with solving PDEs or even ODEs with the Fourier transform, that you only obtain weak solutions and not strong solutions. So that's what we get here, and that's all I have for you. Thanks for sticking with me. I would advise with the Fourier transform that you use your computer a lot rather than playing around with the table, even though the table is very useful, because I don't think I would have wanted to invert this bottom line myself. Anyway, that's all I have. Thanks for sticking with me. I'll see you in class. Bye.